The next section of our lesson in Chapter 17 talks about titrations. We are probably very familiar with titrations from experiences in the lab, realizing a titration is simply using an instrument known as a burette to deliver a known quantity of acid and base to reach neutralization. A couple of handy things our notepack begins by explaining is the term millimole. M-mole for a millimole is 1,000th of a mole. Oftentimes, chemists who work in small amounts prefer millimoles over milliliters instead of the usual mole per liter, since the calculations then are made easier. We rarely add liters of solution through a titration. More often we add milliliters. If you hear the term millimole, at least you have been exposed to it. I tend to stick with the unit we're most familiar with, big M, moles per liter, and simply hit molarity times liter to pull out the number of moles, making the stoichiometry more familiar. But I did at least want to share the term millimole. When we look at adding a solution of known concentration until the substance being tested is consumed, and what that really is showing us is an acid-base neutralization. If I'm adding a base to an acid, the acid gets consumed until it has been neutralized. What this is simply known as reaching the equivalence point. The equivalence point is indeed when the acid ion is equal to the base ion in solution. A graph of pH versus milliliters is simply known as a titration curve. And a great deal of information can be gained by examining titration curves of the various types of acids with bases. So in a titration curve, we can use them, for instance, to determine the equivalence point. By simply looking at where the acid equal base ion, we can find the equivalence point of our solution. And they can also be used to determine the Ka of a weak acid or a Kb for a weak base if they are indeed involved in the titration. So having said that, we will examine three kinds of titrations in our notes. We will examine strong acid versus strong base, strong versus strong. We remember the 7 strong acids, and those that are water-soluble hydroxides create strong bases. Strong versus strong is a unique stoichiometric ratio. So, a second category would be using a weak acid to a strong base. Or I would also classify if we did a strong acid, weak base. But what I'm generally saying here is strong versus weak, either one of those being applied. And the last type of curve that's unique is coming from a polyprotic acid, where we see the ionization of each proton let go one at a time. Strong versus strong, weak versus strong, and a polyprotic acid all have different looks to their titration curves. We will examine in the first part strong acid with strong base. And when I think of strong versus strong, it's really nothing more than a stoichiometry problem in which we determine what the limiting reagent and what the excess reagent ends up to be to determine the pH. The stoichiometry determines the titration curve. Remember, and just to give an example, if HCl is being titrated with NaOH, this would be an example of a strong acid with a strong base. We recognize the single displacement pattern where we produce a salt, NaCl, and water. The important point to note is if the salt has parents that are both strong, there is no hydrolysis from the salt. The sodium chloride will not affect the pH. The only ingredients that affect the pH are the acid and the base on the left side of the arrow. So when I think strong versus strong, it's simply looking at, do we have excess acid and is it controlling the pH? Or do we have excess base and is it controlling the pH? Or are we indeed at the stoichiometric equivalence point where we do not have an excess or limiting reagent and giving us a pH of 7, exactly neutral? So keep in mind there is no equilibrium if both parents are strong. What we're saying is the salt has no effect on the pH as it's forming. And since the acid and base are both strong, they both dissociate completely, giving us a net ionic equation to keep track when an acid ion combines with a base ion and produces water. What controls the pH is the excess reagent as we add additional amounts of either the acid or base through the course of the titration. Let's turn our page and examine further. If we consider a titration where we have a known amount, let's say 50 milliliters of a strong acid, HNO3, and we begin to look at 0.1 molar NaOH being added to it, we can simply analyze the graph into different regions. And let's just examine the pH as we draw the graph down below. So what I'll end up doing is drawing a little graph where we'll place pH units on the y-axis and the volume of base that is being added in our titration on the x-axis, and we'll measure that volume in milliliters. Now, if we're looking at adding base to a strong acid, when I begin placing my pH probe into the solution that's sitting in the Erlenmeyer flask, that would be the acid. So kind of thinking about this drawing, and you know that's my forte, this will be a burette that delivers the base. And that base is exactly 0.1 molar NaOH. So in the burette sits the base, and we have that ready to deliver. Down in the Erlenmeyer flask, we would have, the nitric acid, HNO3, and we happen to know it's 0.2 molar and that it's 50 mils. So initially, we add the phenolphthalein in, and it's clear because we are in the acid solution. So at the beginning point, the initial point on our pH versus volume would be the concentration of the nitric acid. There's been no base added yet. So pH could be found directly by taking the negative log of 0.2 molar, the initial concentration of the acid. And that would just come to us from our pH meter as we placed it in the solution. So imagine having a pH meter giving us accurate measurements, the initial pH found from the concentration of the acid. But as we open up the burette and allow the strong base to enter, we start to notice the pH change. And again, if a base is being added to an acid, it would make sense to see the pH slowly begin to climb. And it will do so as the acid is being consumed. What I mean by that, as the acid is being consumed, we're adding base, taking out the hydrogen ion as we begin to neutralize. So we see the pH begin to climb, and then we notice near the equivalence point, near the stoichiometric ratio of the perfect 1-to-1 amount, we start to see a steep incline. A steep incline means that we're near or perhaps at the neutralization point. And then of course we continue to add base and it begins to level off and we've overshot the end point. So the flavor of a strong versus strong, we start to see a slow and steady rise, shoots straight up high, and then levels off again. What we would notice is right in the middle of this steep incline is the neutralization point, and our pH would be exactly 7.0 when a strong acid is neutralized with a strong base. So I'm examining this curve, and I notice 4 different regions that we could consider as we think about what the pH meter would be telling us. First, we mentioned the initial pH could be determined. And when I think about labeling the initial pH, I'm talking about right here, 0.1, the initial pH reading. And we mentioned since there is no base, the pH comes directly from the concentration of the strong acid. We said up above, since we were looking at 0.2 molar in the first example, negative log of 0.2 gives me that initial concentration's pH. Or suppose we were titrating with the strong acid of hydrochloric. 0.1 molar of HCl would have a pH of 1. So the initial concentration of the acid gives us the initial pH simply because we've not added base yet. Let's consider in the second region where we're between the initial point and the equivalence point. So thinking about that on the graph, 0.1, no base has been added, but 0.2 would be the region. This area, we have yet to reach the equivalence point, but we've begun to add acid. So when we begin to add acid, the pH rises slowly at first, that would be this region, then rapidly when it nears the equivalence point. Notice how it gains a steep curve. In this case, the pH is determined by how much acid has yet to be neutralized. So in this area, keep in mind, we have excess acid, and that amount would be used to determine pH, negative log of the excess amounts. Now, at the equivalence point is the third point of interest. At the equivalence point, right here where we placed an X, we have an exact equal number of moles of base as we do acid, leaving only in solution salt water. And because we know that sodium chloride in our example, both parents are strong, we mentioned it does not hydrolyze, so the pH comes out to be exactly 7. There is no calculation needed. pH equals 7 at the equivalence point of strong versus strong. If we overshoot the endpoint, the pH continues to rise. And that would be the fourth point of interest. Past the equivalence point, we continue to add base. The base becomes the excess reagent. So in region 4, after the endpoint, or after the equivalence point, the pH now is determined by the concentration of the excess amounts of NaOH. So in the first area below the pH of 7, excess acid determines pH. But above the equivalence point, we have excess base that has been added, and that hydroxide ion is going to drive our pH readings to be greater than 7. So that would be negative log of hydroxide, which is POH, and then we would just simply flip it to pH. So 4 areas of the curve that are used really just by stoichiometry to determine pH of a solution at any point in time. Let's model with a sample problem. We are going to calculate the pH for the following quantities when 0.1 molar sodium hydroxide has been added to 50 mils of the 0.1 molar HCl. So equal concentrations, but I'm noticing before and after in terms of the endpoint. Exactly 50 mils, pH would be 7. That would be equal number of moles of sodium hydroxide and hydrochloric acid. So if we had equal amounts, 50 and 50, the pH would be 7. So I would suspect at 49, the pH will be below 7. If you overshoot the endpoint, the pH should be above 7. Let's indeed check our theory. Let's start by considering the stoichiometry. If NaOH is being neutralized by HCl, we understand sodium chloride and water are the products, and this salt does not undergo hydrolysis. So therefore, it has absolutely no effect on the pH of our solution as it's forming. We know we have 0.1 molar of the base, and we're going to put in 49 milliliters of the base. 0.1 molar acid and 50 mils of the acid. Let's do molarity times liters and determine the number of moles and consider the stoichiometric ratio. 0.1 times 0.049 liters gives us 0.0049 moles of the base. 0.1 times 0.05 liters gives us 0.005, and think of that if you'd like to, 49 and 50 in millimoles. What we're noticing is the perfect ratio is 1 to 1. we have 49 millimoles compared to 50 millimoles. We do not have an equal amount, so therefore we have a limiting and an excess reagent. We understand reactants get used in the same ratio. So if we label the smaller of our two answers as a limiting reagent, think of this as before and after the reaction. If 49 millimoles of base are added to 50 millimoles of acid, the acid is in excess amounts. We can simply subtract to find the number of millimoles in solution. 0.0049 from the 0050 gives us the number of excess moles of the acid. 0.0001 moles of hydrogen ion. When I think about writing that in terms of scientific notation, that is 1 times 10 to the negative fourth for the hydrogen ions in excess amounts, and therefore I can hit directly 1 times 10 to the negative fourth, and a pH of 4 comes out. Well below the pH of 7 at the neutral point. So even though that's a tiny number of moles, we still are below the equivalent of 7. If we think about what's happened after we shoot the end point, if we added 51 mils of base, again considering the stoichiometry, we see that if we added 0.1 molar and it was 51 mils compared to the 0.1 molar of 50 mils, and again considering the stoichiometry, we have 0.0050 moles of acid, molarity times liter. And we'll do the same here, 0.0051 moles of base. Perfect ratio is 1 to 1. Now I'm considering a new scenario. It's the acid that is the limiting reagent. It is the smaller of the two numbers. So after the reaction, it's gone. And along the way, it's used up 0.0050 moles of the base, leaving us 0.0001, or 1 times 10 to the negative fourth moles of excess base. However, if I take negative log of 1 times 10 to the negative fourth, that gives us something called POH. The excess amount here is the base. So if POH, 0.001 times 10 to the negative fourth, gives us a POH of 4, the pH comes out to be 10, 14 minus there. So just to consider what's happened. Right before the end point, we are still pretty low on the pH curve. If indeed we had equal amounts of acids and base, pH is 7, but a little bit more base and we see it shooting up all the way to the pH of 10 pH units. So therefore, a significant difference in pH from 4 to 10, which validates that steep slope going from volume of 49 to 51, and we see a rapid rise in the pH. To repeat, if we had 50 mils, that would be an equal number of acid-base moles, no limiting or excess reagent. There is no math to show pH is exactly neutral of pH unit 7. That's the case when, had I delivered 0.1 molar 50 mils of strong base with 0.1 50 mils of strong acid, they are equally consumed. The only thing determining pH then is the water, and it's said to be neutral at 7.0. Of our next page, we begin to consider a second type of titration. Suppose we have a weak acid and a strong base. Weak could be also weak base with strong acid, but we have an opposite pair. Again, we consider the 4 components that are interesting on a titration curve. We would begin considering how we would calculate the initial pH. And again, if I think about what we're setting up, I'll do my best to draw a burette, and in it would be a strong base, something like sodium hydroxide, and it's designed to deliver a precise amount of known concentration of base. Sitting underneath it is our Erlenmeyer flask filled with a weak acid, something like acetic acid or carbonic acid. With a weak acid, the initial pH involves a Ka calculation. For strong acid, it's negative log directly. But since we set up equilibrium with weak acid, it's all about the concentration of the Ka value as well. So with the weak acid, thinking about equilibrium, Hx lets go of an equilibrium process of H plus and X negative, and we would say Ka is equal to the concentration of the hydrogen times the negative all over the molecular form of our acid, Hx. I know the Ka value if I know the identity. X squared on the top over the concentration of the acid on the bottom. When we solve for X, we can pull out pH. These are problems that we have worked all along in Chapter 16, calculating the pH of weak acids by looking up its Ka value. X squared over the concentration of the acid, solve for hydrogen ion. So initially, as we begin thinking about the curve, that would be what it would look like. In between, and I guess how about we come down here as well and kind of start thinking about that in place of the curve. We might as well draw it along. So let's say we're adding mils of strong base down here. Again, volume that's being added as we track the pH up here. So I begin with that initial pH, 0.1. Initial pH is found by using a Ka value. The next region of interest would be below the equivalence point, but past the initial point. So thinking that through, it's the area that I see is slow but steady climb as we're adding base. So it's between the initial concentration, the initial pH, and not quite yet the equivalence point. Knowing that when we have a weak acid with a strong base, we have salts that hydrolyze. Therefore, we have to not only consider the concentration of the acid, but we have to consider its conjugate base that's forming on the product side, and it ends up to be a Henderson-Hasselbalch with a buffered pH solution. So we calculate this as a buffer using Henderson-Hasselbalch equation. And we recall pH is equal to pKa plus the log of the ratio of base over acid. Since we're producing a conjugate pair, if one of them is a weak acid or the weak base, it ends up to be a buffered solution. And because it's being buffered, we start to see kind of a slower, steady climb, and there isn't that necessarily steep view at the equivalence point. As with strong acid and strong base, it was significant, that steep climb, but it is not the case here as buffers resist changes in pH, and that flattens the curve. The third point, I marked with an X, could be found and just stated as the equivalent point. That's when the equivalent amount of the conjugate acid and its conjugate base has indeed equaled. So that actually is equal to the pKa of our solution. When I skim this over, because the salt hydrolyzes, the endpoint is greater than pH of 7 units. Strong acid, strong base, at the equivalence point, pH equals 7. But because we now have to consider hydrolysis of the salt that's being produced, if I add a strong base to a weak acid, the equivalence point is actually over pH of 7. So a greater than 7 equivalence point is how I can determine a pH slope if I'm doing strong base with weak acid. And if I continue to add that strong base after the equivalence point, it's the base then that's in excess amounts. So in excess amounts, it's just the excess sodium hydroxide that's going to determine the pH. We do not use a Henderson-Hasselbalch, but directly calculate the excess amounts of base. Negative log of the hydroxide gives us POH, and we flip it to pH. So considering what we've said, let's take a weak acid, C2H3O2, and titrate it with a strong base, NaOH. And if I think about the product side, we would come up with sodium acetate and water. A net ionic equation leaves together the weak acid break apart the strong base, break apart the salt, and leave together the molecular water. Notice that the acid-base conjugate pair creates a buffered solution in the region between the initial point and the equivalence point. This is a buffered solution, and we have to use Henderson-Hasselbalch to determine the pH. The more base I add, the more conjugate base that forms. The less base, the less conjugate base. And that ratio of Henderson-Hasselbalch, where we know pH is equal to pKa plus the log of the ratio of base over acid, that ratio of base over acid determines the pH in the region below the equivalence, but not at the initial. Remember, the initial is just an old-fashioned Ka problem. Products over reactants, pull out X, where pH represents the hydrogen ion. After the equivalence point, in the fourth region, it's excess base. There is no equilibrium. The excess base ion is going to determine the concentration or pH of our solution there. So again, a little different below as we would calculate after. At the equivalence point, pKa equal pH. So to summarize what we have mentioned, strong acid and strong base is simply stoichiometry. The excess reagent determines the pH. If we have no limiting or excess, pH is equal directly to 7. However, if we have any other type, strong acid, weak base, or weak acid, strong base, weak plus strong, we have to consider first the stoichiometry, then a Henderson-Hasselbalch. And I remember learning just in the buffer system, that's really nothing more than a buffered problem we had worked in the previous section. A weak acid at the equivalence point is equal to its Kb. A weak base after its equivalence is the strong base that's left over. So again, we're just repeating. If we have weak base after equivalence, we have leftover strong base. It will then be determined by using pOH. Let's examine, probably more meaningful is to give it an example. Let's go down to the very last question and consider an example. The first sample problem reads, calculate the pH of the solution formed when 45 mils of a 0.1 molar sodium hydroxide is added to 50 mils of a 0.1 molar acetic acid. Weak acid, strong base. Ka is provided for us, otherwise we would have to use Appendix D. So let's begin by getting a handle of the chemistry. NaOH is the strong base, being added to acetic acid, a weak acid. Strong base plus weak acid. On the product side, we form the conjugate base, sodium acetate and water. We are being told to place in 45 mils of the base with 0.1 molar solution. We are going to place that in with 50 mils of the acid, and it is also 0.1 molar in concentration. What would the pH be at this particular moment in time, a snapshot of this particular titration? Well, let's first figure out how many moles of base and how many moles of acid, so we can determine, do we have a limiting reagent or is it perfect straight on? 45 mils times 0.1 molar can get us something called millimoles, but I like to just use molarity times liter to pull out the number of moles. So I hit 0.045 times 0.1 and I get 0.045 moles of our base. 0.05 times 0.1 pulls out 0.005 moles of the acid. Think of this in terms of millimoles of being 45 compared to 50. The perfect ratio is a 1-to-1 stoichiometric ratio. We have a 45 to 50. So therefore, we have excess amounts of acid, and the limiting reagent would be the strong base. So it determines how much gets used. At the end of our experiment, there is no base left over. All 45 millimoles have been consumed, and along the way it consumed 45 millimoles of our acid as well. So 50 minus 45 would provide us 0.0005 moles of the acid left over. .0005 excess amounts of our acid. Now remember, this salt hydrolyzes. It will also affect the pH. So at the beginning of the experiment, there was 0 amount of the conjugate base acetate, but it gets produced to the same tune as the base that got used, 0.0045 moles, giving us, after the experiment, 0.0045 moles of the sodium acetate, or the acetate in general. Keep in mind what we're trying to pull out is the molarity. The molarity is used in the Henderson-Hasselbalch equation, and these are not equal amounts, so we'll have to consider that. We do an additive volume problem. If 45 mils of base with 50 mils of acid, the total volume is 0.095 liters for both. Also realizing since the volume of the conjugate pair is the same, we could place in the Henderson-Hasselbalch, the millimoles, or the number of moles and still arrive at the same answer. It really is a choice that you could make. So I would probably choose to not divide by the total volume since the volume added there is the same. Let me hit, just to prove that, how many moles of each, 0.0005, and I'll divide by 0.095, and I'm finding a molarity here of 0.00526 big M. 0.0045 divided by 0.095 liters gets me 0.04737 big M molar units. All right, so here we go. pH is found by taking pKa. And pKa is just negative log of the Ka value, and I think I'll just write that directly. Negative log of the Ka provided, 1.8 times 10 to the negative fifth. Plus the log of the ratio of base over acid. We may choose to put 0.0045 over 0.0005, or we could put in the molarity units, and I bet we find the same answer. The molarity of the base, the conjugate base, is the sodium acetate, 0.04737 molar, over the concentration left of the acid after most of it was consumed. We have 0.00526 molar of the acid. Let's hit for the pH of our solution. pH is equal to pKa plus the log of the ratio of base over acid. Let's hit and see what we find. So negative log of 1.8 E negative 5 plus the log of the ratio of 0.04737 divided by 0.00526. And our pH is giving us, for 2 pH units, 5.699. I'll say 5.70 pH units. Just to satisfy ourselves, let's re-hit, not using molarity, but leaving it in terms of mole numbers, just to prove to ourselves that that would factor out. If negative log of the pKa here, 1.8 times 10 to the negative fifth, plus the log of the ratio of base, 0.0045, over acid, 0.0005, can be used directly to find the pH. Let's hit it the other way and compare the work. So, again, negative log of 1.8 E negative 5 plus the log of the ratio of base over acid, 0.0045 over 0.0005. Instead of using molarity, we're just simply putting the number of moles, and we get 5.698. Indeed, the same answer, 5.70 pH units. So, eliminating the step of dividing by additive volume still reaches the same answer of a pH of 5.7. We can see that we're prior to the equivalence point. Strong base, weak acid, the pH ends up to be greater than 7 at the end point, and we're not quite there by this pH reading. Let's examine a next titration problem. We're being asked to calculate the pH in the solution formed by adding 10 milliliters of a 0.5 molar sodium hydroxide, note to self, that's a strong base, and 40 mils of a 0.025 molar benzoic acid. And seeing that they've provided us with a Ka, I'm seeing benzoic acid is not one of our 7 strong, therefore it must be weak and set up an equilibrium. Here we are titrating a weak acid with a strong base. Right away, my mind thinks hydrolysis, and I need the Henderson-Hasselbalch to determine pH. Let's begin first by considering the stoichiometry. The base we are adding is sodium hydroxide, NaOH. I'm not even sure of benzoic acid formula, let's say, so I can simply write that as HA, where HA can represent any monoprotic weak acid. The pattern of change is a double displacement, where we set up sodium benzoate, but I'll simply write that as NaA, and H2O. We realize that the sodium, of course, as parent is strong and will not hydrolyze, but since the anion called benzoate from benzoic acid, the weak acid conjugate base pair sets up a buffer partnership that this A negative will hydrolyze. Benzoate is the conjugate base of benzoic acid. That partnership sets up a buffered system, and you'll start to see the pH resist change. So we see a strong base with a weak acid, stoichiometry first, followed by the Henderson-Hasselbalch. Let's consider what we know. If we have 10 milliliters of a 0.05 molar base and 0.025 molar benzoic acid, and we're placing in 40 mils of the acid into that. So we have a volume and molarity of both the acid and the base. Let's hit molarity times liter and find the number of moles of each of our ingredients, the acid and the base, to determine if we indeed have a limiting and excess reagent. So I will hit 0.05 molar times 0.01 liter, and I find 0.0005 moles of the NaOH, 5 times 10 to the negative 4th, or 0.005 moles. We'll do the same strategy for the acid. 0.025 molar times the volume in a liter, 0.04, and that is 0.001 moles of acid. Thinking in terms of millimoles, we have 5 moles to 10 moles is what that looks like in the term millimoles. Definitely, the limiting reagent looks like the base, NaOH, and the excess acid will be determined in the Henderson-Hasselbalch. So here's what we know then. In the 1-to-1 ratio, the limiting reagent gets consumed, and there are 0 moles of the base left after the titration. Along the way, it consumed 0.0005 moles of the acid. 10 minus 5 leaves us with 0.0005 moles of HA remaining in solution, not yet neutralized. But now also, since the salt that was produced hydrolyzes, it is the conjugate base of a weak acid, it will indeed affect the pH of our solution. Knowing at the beginning of our experiment there were 0 moles of the salt, but the limiting reagent will also produce 0.0005 moles of the acetate, or the benzoate ion. So 0.0005 moles of the benzoate anion have been produced. So here's what we know. The strong base will not affect the pH. It's gone. The limiting reagent completely consumed. But I do have two ingredients, the HA, the acid, and the conjugate base, the benzoate, and both are equivalent values. So if we consider the Henderson-Hasselbalch, we can find the pH by taking the negative log of the pKa, negative log of the Ka provided for us, or using Appendix D, negative log of 6.3 times 10 to the negative fifth, plus the log of the ratio of base over acid. Now what's happened here, we have the same number of moles of the base as we do the acid. 0.0005 moles of our base and 0.0005 moles of our acid. Remember, since the acid and its conjugate base are in equal volumes, we do not necessarily have to convert to a molarity unit. We had checked that in just the previous example, and we determined that we get the same answer if we put moles or we put big M, molarity. When 0.0005 is placed over itself, that simply cancels out, and pH becomes the pKa. And let's hit then. pH will be found by hitting negative log of 6.3, E negative 5. And we're finding a value of 4.20 pH units. Taking a strong base with a weak acid, do the stoichiometry first, followed by the Henderson-Hasselbalch, really is nothing more than a buffering problem from the previous section. Strong acid, strong base, weak acid. Stoichiometry first, followed by the Henderson-Hasselbalch. Let's read our next example. Calculate the pH in the solution formed by adding 10 mils of 0.1 molar HCl. Note to self, that's a strong acid, to 20 mils of a 0.1 molar ammonia, weak base. Strong acid plus weak base. What I'm thinking with strong versus weak, do the stoichiometry first, followed by the Henderson-Hasselbalch. Let's begin by considering the reaction in which HCl, strong acid, reacts with NH3, a weak base. Thinking of chloride really as simply the spectator ion, it might even be helpful to simply write strong acid as H plus with weak base, and I think I'll do that, weak base as NH3, and we can see the conjugate forming then as NH4 plus 1. So here's the weak base and its conjugate acid, setting up the buffered system. If we begin by thinking about 10 mils of the strong acid, and its concentration is 0.1 molar. Volume of the weak base is 20 mils, and its concentration also 0.1 molar. Let's hit molarity times volume and find the number of moles, and we'll consider the stoichiometry. So 0.01 liters times 0.1 molarity gives me a number of moles of 0.001 moles of the strong acid. We're denoting HCl simply as H plus. And 0.02 times 0.1 gives us 0.002 moles of the weak base. Seeing the stoichiometry from our equation is a nice 1-to-1 ratio. The smaller of our two numbers becomes the limiting reagent. The strong acid will be completely consumed, leaving excess amounts of the weak base ammonia. So if 0.001 moles of the acid is consumed, there's nothing left in solution that would affect the pH. The hydrogen ion is completely consumed. We do not care about that when we calculate pH. If it were an excess reagent, it alone would determine the pH, but since it's out of solution, we use it to determine the stoichiometry. So 0.001 moles of the weak base were consumed, giving us 0.001 moles left after the equation. And knowing that at the beginning of our experiment there would be 0 amount of ammonium and along the way produced 0.001 moles of that conjugate acid. So remember, the limiting reagent determines how much of it was consumed for the other reactant and how much of the other product was actually made. So here we're noticing again the amount of the conjugate pair being equivalent. And when we think about the Henderson-Hasselbalch, pH will be determined simply by pKa when the conjugate pairs cancel. So pH can be found by the negative log of the Ka value. Now notice, ammonia is a base. When I look up a Kb for ammonia, it is 1.8 times 10 to the negative fifth. Henderson-Hasselbalch requires a Ka value, not a Kb. So I simply take the ion product constant for water, 1 times 10 to the negative 14th, and I place it over the Kb value of 1.8 times 10 to the negative 5. Ka over Kb inside of this parentheses does indeed flip it to a Ka constant, plus the log of the ratio of 0.001 moles of our conjugate base over 0.001 moles of the conjugate acid. Base over acid moles drops out because they are equivalent. So pH can be found directly by taking pKa, and let's hit the negative log of 1e negative 14 divided by 1.8 e negative 5. Remember, what we're doing in this parenthesis is taking Kw over Kb to convert to Ka. Henderson-Hasselbalch requires a Ka value. And when I hit, the pH is 9.26 pH units, which makes sense. We're in a basic range. Up above, we were titrating in the acid range, and we came out with a value below 7 of 4.2 up there. Alrighty. So here we had an example of strong acid with weak base, again Henderson-Hasselbalch. Just to compare, I'm noticing that if I'm given a weak base, it's still a base over acid conjugate ratio, but the only difference is that I had to flip Kb to Ka to get Henderson-Hasselbalch to work. Alrighty. Let's take a look at try these in the next one. Calculate the pH at the equivalence point. The very definition where moles of acid equal moles of base. We're titrating 50 mils of a 0.1 molar acetic acid, which is a weak acid, with 0.1 molar sodium hydroxide, a strong base. Weak acid with strong base at the equivalence point. Well, let's take a peek at what that means. If we have acetic acid, HC2H3O2, sodium hydroxide, NaOH, weak acid with strong base. Just think of a double displacement where water is produced and the salt of sodium acetate, NaC2H3O2. If you eliminate the spectator, which we might as well, we end up seeing a conjugate pair form between the acetic acid and the acetate ion. So acetic acid, weak, strong base, produces water, and the conjugate base called acetate. Let's keep track of what we know. If we have 50 mils of the weak acid, its concentration is 0.1 molar. The concentration of the base, also given as 0.1 molar. The very definition of the equivalence point is the number of moles of acid equal the number of moles of base. There is no limiting or excess reagent. That both are equally consumed. So when I think about the number of moles, I would simply hit 0.05 times 0.1 is 0.005. And I also know that that must be the same value of moles of the base. The equivalence point means equal parts acid as base. And that also means, since we have equal concentration units of 0.1, that I must have also added 50 mils of the base to deliver the same number of moles, 0.005. The 1-to-1 ratio is being met perfectly. 0.005 moles equally consumed, leaving 0 amount of the acid and 0 amount of our base, but it also produces 0.005 moles of the acetate ion. This is a conjugate of a weak acid and will hydrolyze. It turns into a hydrolysis problem. So at the equivalence point, the only thing affecting the pH is this negative acetate ion, and it's doing so through the process of hydrolysis. And from our last chapter, we remember hydrolysis is when we take a salt, and this really was sodium acetate. The salt, whose parent comes from a weak acid, hydrolyzes to make the solution basic. We go back to forming the conjugate acid of acetic acid, giving us hydroxide ions in solution. So the acetate is pulling off a proton from the water, and when it does so, the solution becomes slightly basic. When we calculate our pH, our answer had better show the base range, since I'm seeing hydroxide in the formula. When I think about what we need an initial concentration of the acetate, knowing that we can call acetic acid X and the hydroxide X. What I know from over here in the titration equation that we produced 0.005 moles of acetate. But I need that to be in a molarity unit to carry over for a KB problem. So I think about the combined volume. If 50 mils of acid were put into 50 mils of base, we end up with 0.1 liter, 100 milliliters. So when I carry over the initial concentration of the acetate to the hydrolysis problem, I'm going to show that as a molarity of 0.005 big M. What I also need is a KB value, since this is showing a basic equilibrium. There is no KB on our Appendix D for acetate, but I can find the Ka for acetic acid. Let's take the ion product constant for water, 1e negative 14, place it over the known value for acetic acid, 1.8 times 10 to the negative 5th, and there's the conversion, Kw over Ka, finding Kb. We'll set that equilibrium constant equal to x squared, where x is going to stand for hydroxide and the value of the acetic acid. Set over the molarity of 0.005, the amount of acetate produced from the titration problem. Let's solve for x. So we'll start with 1e negative 14 divided by the known Ka value of acetic acid, 1e negative 5. 5.56 times 10 to the negative 10th is now the value of Kb. We'll cross multiply with times 0.005, the molarity of our acetate solution. That's equal to x squared. So square root my answer, and we're finding x equal to be 1.67 times 10 to the negative 6th. Remember, that's the value of hydroxide. We are in a Kb, a base equilibrium. So to pull out pH, we'll hit 14 minus, parenthesis, negative log of that hydroxide concentration, 14 minus POH, and we find a pH of 8.22 units. Does that number make sense? Well, yes, it does. We're above 7 on the pH scale, knowing that we're showing an equilibrium that's producing a base ion. This number lies in the base range, 8.22 pH units. Now I think I made a mistake. I'm going to come back. If you're still listening, if I cross-multiplied here 0.005 divided by 0.1 turns this into 0.05 molar, which turns this into 0.05 molar. And let me re-hit. Boy. All right, so starting over from the drawing board, 1e negative 14 divide by 1.8 e negative 5. And I'm sorry if you caught that and wondered what I was doing. So let me catch up to what I'm sure you've already done. Found the correct value of x. 5.27 times 10 to the negative 6. Adjusting for my decimal error. So 14 minus, parenthesis, negative log of that answer finds a pH of 8.72 pH units. And that is the correct answer. Calculating the pH at the equivalence point when acid moles equal base moles. We'll consider benzoic acid, I'll write as HA. It's a weak acid with a strong base of sodium hydroxide. I'll eliminate the spectator and just simply show OH negative. What I see forming here is a neutral water and the conjugate base called benzoate, A negative. Now at the equivalence point, the number of moles equal for acid and base means there is no limiting and no excess reagent. Therefore, the only thing affecting the pH is the hydrolysis of the conjugate base coming from the benzoate ion. We'll need to determine the number of moles produced divided by the combined volume. Let's begin by keeping track of what we know. We have 40 mils of the acid and its concentration 0.25 molar. Let me hit molarity times liter to find its number of moles. 0.04 times 0.025, I'm finding 0.001 mole. We also see the concentration of the base to be 0.05, big M, molarity. And what we also know is the number of moles, 0.001 moles, the very definition of the equivalence point. Acid moles equal base moles. What we have to determine is the amount of base it took to reach that equivalence point. So, since the moles are equal, it can simply be an MV equal MV. The molarity and volume of acid equal the molarity and volume of base. That's only true at the equivalence point. So what we find is the molarity and volume set equal to molarity and volume. We can pull out the missing volume of our base. 40 times 0.025 equals, and then we'll divide by 0.5. So we added 20 milliliters of the base. The number of moles equally consumed means afterwards there's no excess amounts of acid, there's no excess amounts of base. The only thing affecting it, the pH that is the hydrolysis of the negative benzoate ion. So if the limiting and excess reagent doesn't play a role, it turns into a hydrolysis problem. And we produced 0.001 moles of this conjugate base, A negative, has a name of benzoate, in a new combined volume of 60 milliliters, or 0.06 liters. When we hit 0.001 mole divided by the 0.06 liters, we find the molarity of 0.167. So if I consider the hydrolysis of benzoate, where benzoate is coming from sodium benzoate. Sodium benzoate is the salt. We eliminated the spectator and are simply showing A negative. It pulls a proton off of water to form benzoic acid again, leaving a base ion in solution. When we are done calculating, we better have a base pH. We've determined the initial concentration of this to be 0.167 molarity units. What we also need to find is a Kb value for benzoate. And remember up above, we were given Ka for benzoic acid. We'll just simply convert Ka into Kb. So we'll start by saying 1 times 10 to the negative 14th, there's the Kw, set over the Ka for benzoic acid. Kw over Ka is the Kb we need for this hydrolysis. That'll be x squared over 0.0167 molarity units. When we find x, it will represent the hydroxide ions in solution. We find Kb by taking Kw over Ka, set equal to x squared over the value of 0.167. Let's hit for the value of x, knowing that that's a base ion. 1e negative 14 divided by 6.3 e negative 5. And my Kb value now 1.59 times 10 to the negative 10th. Cross multiply with 0.0167 molar, and that's x squared. So I take the square root and we find the value of x to be 1.63 times 10 to the negative 6th molarity units. From there we can find pH. 14 minus the negative log of our hydroxide, and our pH comes out to be 8.21 pH units. At the equivalence point, equal amounts of acid and base are consumed. The only thing affecting the pH is the hydrolysis of the negative ion. Let's look at our last example on our titration, page 9 of the notes. We are being asked to find the pH at an equivalence point when 40 mils of ammonia is titrated with 0.1 molar of acid. Here we have a weak base, ammonia, with a concentration of 0.1 molar and a volume of 40 mils, being titrated against a strong acid, HCl. And again, the chloride serves as a spectator, so let's go ahead and denote just H plus as the value of hydrogen ion, 0.1 molar. I know at the equivalence point we have an equal number of acid moles as base moles. And on the product side, we are forming the conjugate acid of ammonia, called ammonium. The very meaning of equivalence point means equal number of moles of base as equal number of moles of acid. Molarity times liter for the base shows us a value of 0.004 moles of ammonia. Knowing that the equivalence point means equal parts acid and base ion, we also know we have 0.004 moles of H+. Molarity times volume equal molarity times volume in the equivalence point, so we could also determine a new value for 40 mils of the hydrogen ion. Now, since we have equal numbers, there is no excess amounts of acid or base, giving us nothing on the left-hand side that will influence the pH of this solution. The only thing left to influence is the ammonium conjugate acid of the ammonia, the original base. Knowing that 0.004 moles equal value of acid and base would produce 0.004 moles of this ammonium ion, we'll divide that by the new added volume, 80 mils or 0.08 liters. And let's solve for the new molarity, 0.004 moles divided by 0.08 liters, and I'm showing that to be 0.05 big M molar units. If we know the concentration, too many zeros, if we know the concentration of the ammonium, it now simply turns into a hydrolysis problem. Again, the left-hand side are completely consumed. It's the ammonium that goes on to hydrolyze, going back to form the ammonia in an acid protonated water called hydronium. Our pH had better end up in the acidic range in this hydrolysis process. So here's what we know. This is an acid equilibrium for the hydrolysis of ammonium. We look up ammonia and it has a Kb, but we need that to be a Ka to represent this hydrolysis. We'll use the ion product constant of water, 1e negative 14, over the known value for Kb of ammonia, 1.8 times 10 to the negative 5th. We can find that in our Appendix D, or perhaps we've used it just enough to where you're beginning to memorize. Ammonia and acetic acid share the same value for Ka and Kb. So in our parenthesis, we have determined Kw over the known Kb of ammonia. We'll convince that to be a Ka. We'll set that equal to x squared over 0.05 molar, where x is going to stand for the hydrogen ion, which can then be used to find pH directly for the acid proton. So we'll hit pulling out x. So 1e negative 14 divided by the known Kb for ammonia, 1.8 e negative 5. It has now been converted from a Kb into a Ka. We'll cross multiply by the 0.5 molar concentration of the ammonium ion, and now that's equal to x squared. Square root my answer, and hydrogen ion is looking as 5.27 times 10 to the negative 6th molar units. Negative log the hydrogen directly, and we get a pH of 5.28 pH units. That definitely makes sense. We are showing a hydrolysis of an ammonium producing hydronium, and 5.28 is in the acid range.